Hello and welcome to the course Design Borefields with Confidence. This is part 1, chapter 2, Why should I care about borefield design? Because we already talked last time about the advantages of a ground source heat pump, the efficiency, the passive cooling and so forth. But this of course only is true when the borefield is designed correctly. So in this section, before we talk about the actual design later in this course, we will focus on why should you care about the design of borefields specifically, and what different ways are there to design a borefield. So when we talk about borefield design, we're talking about temperatures. Now, the rest of this course will be about these temperature plots, so don't be afraid if not everything is clear at the moment. But in fact, what you see here is a temperature profile, temperature on the y-axis and time periods on the x-axis. And what you see, it varies from season to season. So in summer the temperature rises because you're injecting heat in the ground, and then in the winter it cools down because you're getting the energy out of it. And this blue line is the fluid temperature circulating through your borefield. Now, the idea of design is that these temperatures, these fluid temperatures, should stay within certain limits. And you have a minimum and a maximum limit. Now here it's 2 and 17 degrees. But depending on your country and your experience, these limits might vary a little bit. Now, the philosophy is that the minimum limit can be for legislation. Perhaps there is a standard in your country, so you have to design according to certain rules. Typically, it's 0 degrees as an average fluid temperature in your ground, or perhaps it's 0 degrees going into your ground inlet temperature. If you're, for example, working with water, there is a risk for freezing, so you want to stay above this 4 or 5 degrees inlet fluid temperature. So perhaps there is a standard for it. There is a sustainability reason for it also, because if you freeze the ground, that's not good for the microbiological life in the ground, for the ecosystem there. So you want to stay away from negative and freezing temperatures. But also freezing itself is not good because of efficiency reasons. Because ice is an insulator, and when there is freezing and there is ice around your borehole, it basically gets insulated from the rest of the ground. So it becomes really hard for the system to extract energy from the ground, and your system performance will drop, your electricity costs will increase. So please stay away from that. It's even possible that your system will fail in the end if it's not able to extract any heat anymore. But also, depending on the type of grout you're using, having negative temperatures for a longer period can cause this grout to crack because there is moisture in it. And when this moisture freezes, it causes such an internal pressure that the grout may crack and that your borehole actually gets damaged. And if this repeats season after season, in these cracks, groundwater comes, it freezes again, it cracks more open, and you're ending up with a borehole that has a totally cracked grout, and then also the heat conductivity is no longer guaranteed. So that's an important thing. Please stay away from these negative temperatures. The maximum temperature, you also have legislation around that in some countries. For example, you do not want more than 25 degrees going into your borefield. Also for sustainability reasons, again, it can disturb the ecosystem in the ground. But also if you go to too high temperatures, 40, 50 degrees, for example, there starts becoming a problem that the mineralogical structure of the ground starts to change, because some minerals start to dissolve in warmer water, and your geological condition is basically changing, which is also not something you want from a sustainability point of view, where you want to limit the impact you have on the environment. And thirdly, cooling capacity is also important, because if you say, well, we want to use passive cooling, then typically, you cannot go above 17 degrees on average in the ground, because imagine you go to 20, then you have 21 on your building site, and you cannot cool with that anymore. So with passive cooling, there's a rather strict limit, typically between 16 and 18 degrees average fluid temperature. And the last problem is with leaks. So plastic, it becomes longer or it stretches with temperature. There is a temperature variation there. So if you have quite long horizontal connections and your temperature fluctuates quite a lot, yeah, then your pipes, they stretch and they shrink again, and this can cause leaks in the welds over time. Now, if you stay below 25 degrees, that is typically no problem, but if you go to 30, 40, 50 degrees, for example, if you're in a very warm country, yeah, then this expansion can become significant, and perhaps it's a good idea, at least for the horizontal connections or for the welds, to opt for a plastic material that is more capable of withstanding these warmer temperatures, because your typical geothermal probe, the plastic there expands quite a lot. So for the horizontal connections, please pay attention to that there are no too many stresses on the welds itself in order to prevent leaking over time. So that's the philosophy of design. We want to stay within certain limits. These can vary a little bit from case to case, from country to country, but in the end, there is always the goal of staying between limits. Now, we want to do that by borefield design. So determining the depth and the number of boreholes, as well as other parameters we will discuss later this course, but the goal is to determine the required borefield size such that we stay within these limits. Now, we can do that in two ways, basically. On the one hand, we have rule of thumb. Here we say, okay, we have a specific heat extraction and injection from experience, and we know that our borehole can deliver 30 to 40 watts per meter. If you do that and you know your peak power of your building, for example, it's 3 kilowatts, then you know, well, we need 100 meters of borehole length in total. So that's the rule of thumb. And on the other hand, we have what I call reality. Not every project is the same. Soil conditions can vary from location to location. The ground conductivity can be different. You can have different borefield configurations. One project can be deeper boreholes, the other one shallower, more dense together, more apart. We have laminar or turbulent flow rates in our boreholes itself. We have different types of antifreezes that you can have. You have different imbalances of different buildings. You have perhaps a different peak in cooling than in heating and so forth. And this whole reality you're dealing with when you're a borefield designer is not captured in this simple one number that determines your total borefield size. And even when this is clear, rule of thumbs are still used quite a lot in industry. Which is why we decided to do some research about it, and we simulated 3 real-life buildings, an auditorium, an office building, and a residential building, in a dynamic simulation software to get a really precise hourly profile out of it. So we know the heating and cooling demand of these buildings at every hour. And what we then did is, for each of these 3 buildings, we varied all the input parameters you will encounter in your daily borefield design life. Namely, we have a good conducting soil or a bad conducting soil. We are going to drill deeper or shallower. We're going to use active cooling or passive cooling. We're going to use water or antifreeze, and so forth and so forth. So we end up with quite a lot of variations, and for each of these real situations, we determined the required borefield size, and we put that next to the design we would have when we just simply used 30 watts per meter. And the results are seen here. So what you can see is every red dot is a real simulation. It's a real situation that you can come across when we install the same building at each of these different project locations. And you can see that for the auditorium, depending on design choices you as a borefield designer can make, your design is somewhere between 1,000 and 5,000 borehole lengths. Whereas for the office, it's between 5 and 23,000, for example. So there is an immense range determined by factors you as a designer have influence of. Whereas if you, for example, look at your rule of thumb, your 30 watts per meter, if you apply it to the peak power, you get the orange arrow. And if you apply it to the peak power in cooling, you get the blue arrow. So what you can see there is, if you work with this rule of thumbs, you get just one number, and you don't see the variety or the flexibility you as a designer have when you're working with borefield design in general. So it gives you a total unnuanced view of what is actually possible with this solution. So perhaps you can say, okay, perhaps my 30 watts per meter is just wrong and I need another number. So what we can do is we can take these different red dots and the total borehole length, divide them by the peak power, heating and cooling, and then get the same figure but for the specific heat extraction. So basically reverse engineer your rule of thumb. And that looks like this. So you can see that your rule of thumb should be somewhere between 40 and 240 watts per meter, depending on geological conditions, design choices, and so forth. So basically, it's just not feasible to end up with one figure that works for every location, every borefield design, and every building. It's just not feasible. And that's then basically also the conclusion of this. Why should you care about borefield design? Well, borefield design talks about we want to stay within temperature limits. Rules of thumb are a shortcut. It's not calculating anything. It's just one number and a linear correlation. And if you use this rule of thumb, you're basically ignoring these temperatures. You're taking a shortcut. And since you're ignoring these temperatures, yeah, they can also not be trusted. It's not trustworthy because you do not know, since you did not design anything, where you're going to end up. So I hope it's clear that the goal of this course, or the reason this course exists and that you're watching this video, it has a purpose. The purpose is design borefields with confidence to end up with systems that are not oversized and economically infeasible, and also not undersized so that comfort can be guaranteed in the building and in the project you're actually designing. So now we have all the knowledge, we know why we are following this course. Let us start in the next chapter with talking about the input parameters. Let's talk about the ground.